Hello, everybody. Good morning, good afternoon, depending on where you're joining us. Good morning for you, Nick. How are you?
Good morning. Doing well. How are you, Laura?
Good, good. Here, well, I'm based in Spain. For us, it's 5 p.m. So yeah, almost over for the day.
And quite the opposite here. It is 8 o'clock my time here on the West Coast in the US. So good morning.
Good morning. Nice time difference. Thank you for joining us this morning. It's quite early for you, so thank you.
Yeah, absolutely. Glad to be here. I'm sure plenty of our friends over on the East Coast are well into the day, so really a wide range of time frames here.
For sure. Nevertheless, this is going to be live, so if you have any colleagues who are missing it, they can always just watch it later. So perfect. Okay, we're 1 minute from 5. We can start. We'll begin slowly, so if anybody's just joining, they're right on time. So thank you everybody for joining us. Today, my colleague Nick and myself are going to talk about conquering grid saturation, okay? And specifically, we're going to go into capacitor banks, battery storage, overhead lines, and more. So just quickly about us. I'm here with my colleague Nick and I'm Laura. I'm from the business side of RatedPower. I've been in the company for 4 years almost. And well, yeah, business side, specifically Oceania region. Nick, if you want to go ahead and present yourself.
Yeah, hey again, everyone. My name here is Nick Opdahl. I am a power and renewables principal consultant here with the Inverter team, working with a couple of different products, energy acuity for those that are familiar with those kind of more legacy systems, Prism, and of course, pvDesign, which we'll be talking about today. Really passionate here about engineering any sort of renewable technologies, and of course, grid reliability, as we'll be talking about today.
Perfect. Looking forward to it. This is more or less what we're going to go through today. We're going to start by why are we talking about this today? What is grid saturation, challenges and solutions? And then my colleague Nick is going to go into pvDesign and actually show you some of these features that we can engineer in pvDesign. And then we're going to have a Q&A session long enough. So for sure, you have, I think, on the right side down, a question section. Feel free to ask any questions and we'll go through as many as we can. We can't cover all, which would be really nice. That means that you have a lot of questions and you are finding this interesting. Then we will answer them later. No worries about that. But let's start. So trends report, basically, why am I mentioning this? We got the idea of talking about this today because of this trends report that we do annually. Here we ask many professionals in the industry, we analyze our designs in pvDesign too, more than 10 terawatts of designs in more than 20 countries. And what we found out is that of all of these designs, well, one of the top things that was a common factor on everybody that answered our questions was that the biggest challenges of the sector are grid saturation and instability, followed by permitting and regulation, which is in the end quite related, right? So that's why we thought about talking about it today and how can we provide solutions to that challenge. So we're going to start focusing on grid saturation, of course. So what is it? What's grid saturation? Well, just average description, basically, grid saturation refers to the level of electricity output carried on the distribution grid. We can have high grid saturation, which occurs when there is more power generated than the grid can handle, which of course in the end, it causes the grid to become unstable, and it could even force grid operators to curtail electricity generators, right? On the other hand, we could also have low saturation, which would occur in areas where there might be not enough power generation to meet demand. Nevertheless, that's today we're going to talk mainly about high grid saturation. Let's talk about the challenges. So what do we mean by challenges? Well, high grid saturation is increasingly posing problems for grid operators as they try to manage the uptake of all the renewable energy in the sector, right? What are these challenges? So we can mention the fact that it's a fast changing sector, which make it really hard for operators to keep pace with the upgrades to interconnection capacity needed. But also this needs to be tied up with technology upgrades. And for example, I want to put here an example that we see is the fact that power grid distribution systems were actually designed to carry power flows only in one direction, right? Traditionally, it would go from generation sources to consumers. But the growth of distributed solar and wind installations requires grid to accommodate actually two-way electricity flows, as consumers can also send electricity to the grid. So, I mean, not only that, but also these flows fluctuate rapidly, which results in substantial changes in the amount of electricity flowing through the grid. Imagine how hard technically that is. Just to put some numbers in it, in Spain, for example, according to Red Eléctrica, which is our publicly grid operator, 2% of the energy generated is actually thrown away, and this is expected to increase to a 5%. And this is only in Spain. Imagine other countries too. Other thing that we could mention in terms of challenges would be how grids are publicly owned a lot of times, right? And as we know, also public things sometimes tend to have slow investment. So it's something that could limit how fast a grid can be upgraded. To mention more things, we could even go into outdated equipment. Voltage regulators that were installed decades ago are no longer fit for purpose in modern energy systems. Apart from that, negative energy prices also affects investment confidence, which is also a challenge, which is not helping solve our grid saturation problem. And last but not least, also just to mention, permitting and regulation holdups. Grid operators don't have enough data to assess the impact of grid saturation, therefore holding up project approvals, awaiting interconnection studies and upgrades, which often results in energy regulators often having to put directly a cap on new solar and wind installations. In the end, it's all related, as you can see, and it's all imposing great challenges on the grid. So we're going to go ahead and mention some of these solutions to today's power grid challenges. And I think we can all agree that some of these are what we're seeing here, right? Battery storage, capacitor banks, substation design, and overhead line. These are things that have been working in other markets and that often governments may require for new projects. We've seen this in many different markets. For example, Australia is one of the markets that I know more because of my position, but we know that is common in other markets how new projects are required to include a battery storage area. So it's interesting to see. Why or how, let's say. Battery storage, in particular, let's start with this one. It's key to limiting grid saturation and maintaining this grid stability. As you know, batteries can store excess solar generation and release it later when it's needed. Furthermore, it also prevents overloading the grid with excess supply. In the end, energy storage can operate as part of a smart system to automatically control electricity flows and increase this energy efficiency. So that's battery storage. Nick for sure will talk later more about it. Other part would be capacitor banks. Capacitor banks provide a stability and clean, reliable power as it directly influences the power factor, making sure that the power we are outputting is sufficiently clean and useful to transport it to over the lines. So again, we'll see how pvDesign can help you on this design. Last but not least, overhead line and substation in general will help the challenges of grid saturation by increasing investments and pushing for a faster engineering, construction, and optimization of the design and costs, right? This is where pvDesign can be a great tool. Defining a new overhead line will provide, in the end, grid modernization. We have to think about what we have, and in this sense, many transmission and distribution lines around the world are reaching the end of their lifespans or cannot accommodate new renewable energy, right? However, installing new lines and modernizing this grid infrastructure is costly. That's why the more digitalization, the more fast engineering that we can put in it, the better. Similarly, substation design is another output or generation source that plays an important role in modernizing and maintaining stability through the grid. So I think Nick will go ahead and have more technical information about all of these methods, why might they be helpful, and how to design them in pvDesign. Get your questions ready, okay? And just write in on the question chat, and we'll get through them at the end of the presentation of pvDesign. And with that being said, I'm going to go ahead and let Nick start presenting. Thank you for listening. And again, any questions, feel free.
All right, awesome. Thanks, Laura. Great introduction here, great piece of info on the market as a whole, as well as kind of those last tidbits on overhead lines, BESS, substation, and of course our capacitor banks, all playing a different role, but in combination really going to help us in terms of the grid saturation, whether it be on the high or low end here. So hopefully everyone can see my screen here now. I am in pvDesign looking at the grid point section. In particular, here you can see where I have an example solar site here set up, PV plant, where I have my panels, a couple restricted areas, my AC BESS coupled system, and then here in purple is our substation. Also in pvDesign, we do have the ability to go ahead and actually design into overhead lines, which you'll see here by this kind of faint red line. I'll go into this in more detail. We can define that path to wherever it may go. And in this case, I found an adjacent substation just maybe a couple of miles away into, say, the larger grid where we might actually interconnect in a real case. So recentering us back here on our project site. Again, I'm over here in the grid point section, checking out the actual connection type, where I'll first begin talking about the substation. So in talking about grid saturation, really the first and foremost things that we need to consider here are actually going to be our substation or POI, as well as our transmission line, since that's the supporting infrastructure that's actually going to allow the electricity to flow into the grid as a whole, both in and out of our generation plant here, assuming that we're using, say, a BESS solution. So discussing that substation and transmission line, since they're both the electrical equipment, that's really what's going to allow our capacitor bank and BESS system to help further go ahead and clean our power and make sure they're effective in reducing both the congestion as well as the grid saturation here. So again, going into grid point in connection type, we can choose exactly what standard that we're going to use. IEEE being very, very standard here in the US, whereas IEC might be standard here kind of in the rest of the world. So just choosing whichever one makes the most sense depending on what region that we're actually designing in here. For my US folks, I know that the IEEE here is very common and something that's kind of near and dear to my heart here as some standards to go ahead and design with. Next, we're going to have our couple of different choices here. So we can select the standard, and then of course we can choose our limits in terms of our amperage for our medium voltage collector system in the line, as well as our medium voltage level. Here I've selected just a couple of standard values. Maybe we select 500, maybe we select all the way up to 1,000 amps. And then our medium voltage level, things that you would see normally in the industry, like 14, 21, 34 and a half, or really anything in between, but just thinking here of what the grid actually might look like and what standard equipment might choose here. So now we're going to be thinking about our actual interconnection facility. So technically in pvDesign, we do have two options. The first one here being the switching and breaking station. So this is if we're just going to be essentially implementing a smaller solar site, say going to the distribution grid and being a more localized project, if you will. Whereas the second one here, the one that we're going to be focusing on today, being the actual substation, again, for transforming up to higher voltages and going to the transmission grid to be distributed really on a larger scale level, as well as being able to absorb higher amounts of power here. So this is the one that we'll be looking at today. Just a quick comment, you might have noticed that the switching and breaking station has been grayed out in this case. If we have a sufficiently large site where pvDesign essentially lets us know that, hey, for the size of the plant, it doesn't really make a whole lot of sense, both in the terms of building it out, structurally wise, electrically wise, and maybe fiscally, having a switching and breaking station, pvDesign will kind of have some guardrails for us, letting us know that substation really is our ideal choice from an electrical and civil perspective here. In combination with that, we're going to look at the actual substation arrangement. So we have a few different options here, as you can see below. All these are optional. If we don't choose it ourselves, pvDesign is going to utilize the different algorithms and calculations in the background to choose the one that's best. But here we can choose whichever one we like if we want to do that manually. So in selecting our choice here, you can see that under substation, we have two different arrangements, either a single bus bar or a double bus bar arrangement. Now, single bus bars, of course, are going to be less costly and use less equipment, but thinking here about grid saturation and reliability, having a double bus bar will provide that level of stability and reliability within the sub. And also, if we plan on expanding the sub at any point, or say injecting a larger amount of power by absorbing, say, more energy over the grid, say our BESS is going to be used as a sink as well as a source to the rest of the grid, it might be pertinent for us to use that double bus bar arrangement here in planning for that sink of power, as well as any kind of expansions to the substation as a whole. If we're in talks with, say, our local utility, saying we want to build out a sub that can be used more than just for our point of generation, but really a place where transmission lines can run through. Of course, that all goes through those initial planning stages and talks with the utility, but something that should be considered and would be talked about in the initial development here of the project. Next, looking at the high voltage level, again, pvDesign is going to provide us some general guardrails as to what we should kind of aim for here based on our size of the site. Here you can see that it's recommending at least 230 kV on the low end and 550 here on the high end. Again, under the assumption that I want to really build out my site to be robust and a point of interconnection where we can help with grid saturation and charge and discharge our batteries frequently. I'm going to go ahead and size up maybe to another US industry standard here of 345 kV, allowing for extra power to be dispersed here at my POI. And then I won't get into the details here because I want to cover the rest of the content, but we do have the ability to select our power transformer type, say 2 or 3 winding. We can size our power transformer manually if we like, and set our output bays accordingly. Or again, if I just want to let pvDesign run the rest by itself and perform those calculations on my behalf, I can just open those up here and let pvDesign do the work. And clicking Run Design, we're actually going to see those electrical outputs come out over here on the right-hand side with our changes in terms of our connection type. So of course, having a substation is great, and having one built out that's going to have essentially some extra headroom electrically is an important part of reducing kind of that grid saturation and preparing for the expansion of our grid. But really what we need to do is we can't have any, distinct choke points allowing us to reduce our overall power being transferred. And that choke point that I'm potentially talking about here would be second in terms of the overhead line. So in selecting the overhead line, we have a few options here, both in choosing, say, our circuits and conductors per phase, what our actual phasing conductor will be, tower shape, and earthing wire, which all play a direct part in terms of the sizing of the transmission line, making sure that it's up to our spec and up to the level that we need to actually transfer our anticipated amount of power over this line. And again, pvDesign, using the IEEE and other handbooks here to provide some guidance, we can see already that it's providing us a warning, telling us our electrical criteria for the design might not even be met in the singular case that we have now. Of course, this would apply as we're planning on expanding out into the future. So it's suggesting that we increase the number of conductors per phase. Here, I'll just maybe say select 2. And let's see if that goes away here in the background. I'm just going to run my design real quick. And if that doesn't work, maybe I'll go ahead and add a 3rd conductor per phase, or alternatively, I could increase the sizing of my phasing conductor, or in combination, that would help me in terms of sizing for that added power over the line. Something else to consider too is this option here of capacity overestimation, where we can essentially size an extra or kind of a safety factor, if you will, over the actual estimation of energy that's going to be transferred over the line. Again, and thinking about the reliability of the grid saturation, and expanding it as a whole, perhaps in tandem and working with a partner as a utility, we can here design and say we want extra capacity over our estimation to the tune of whatever number we'd like. Again, maybe we're planning an expansion here in the near future of say 5 or 10 years of at least 50 extra MVA being transferred over the line. We can give, say, plenty of headroom, or maybe if that's too much, we can just set a factor here of, say, 25 MVA to be considered in sizing up the line and making sure that electrical and civil design adheres exactly to that change. Again, like I said before, we can always size up the phase conductor here if we need to, choose whatever tower shape that would be implemented in practice. Again, this would probably mirror whatever you're going to see interconnected into the actual grid at large. And then lastly here, choose our earthing wire or a ground wire for those of us in the US. Again, making sure that we're able to disperse in case of any sort of electrical hazard that occurs. Moving on here to the grid requirements. This, of course, talking directly to the capacitor bank and the power factor as a whole. Of course, here in pvDesign, we have the option to actually select and make sure that we're sizing our plant and equipment in accordance with our power factor here. I've been really excited to talk about this because this is actually a newer feature that just recently came out over the last, say, month or so in pvDesign, is the implementation here of capacitor banks. So before, we were only able to correct the power factor and set a required power factor using inverters only. So those actual inverters sitting within the PV plant. Whereas now we have the choice to use a combination of both the inverters and the cap bank itself. In this box below, I can set whatever my power factor is. Maybe that's based on a PPA agreement. Maybe it's an agreement with the utility. Whatever it may be, we of course want to make sure that the power that we're injecting into the grid is sufficiently clean. One, for regulation purposes, but two, again, getting back to the point of grid saturation and reliability here. The cleaner the power that we're able to distribute over the line, the more that it can actually be used by our end users. So commercial, industrial, even residential. Any sort of dirty power that we have, of course, cannot be used by those end users. And so having a clean and reliable power transferred over the line will maximize really the amount that is able to be transferred and absorbed and used by those different end cases here. So let's say we have an agreement with a, say, utility or a PPA in place to make sure power is extra clean here. Let's say we're shooting for at least 0.98 at our point of interconnection. So I'm going to set that in this case. Now I have the ability to define the strategy settings. And what I mean by that specifically is we can say exactly where we want the inverters to compensate for this required power factor of 0.98 and where we want the actual capacitor bank to compensate for that. So we can see here with a color code, the inverters here in that kind of tan color is saying where the inverter is going to try and compensate for that power factor. And same thing here with a blue in the capacitor bank saying where our cap bank that we're going to insert is going to be compensating for on the line. Let's say that I'm just fine with our inverter compensating for essentially add our inverter output here to our substation input. Then I'm going to size my capacitor bank and make sure it's in accordance here, going ahead and cleaning and compensating for that extra reactive power over the line at the actual substation input all the way to the grid. So this is taking into consideration those transmission lines, the length and the build that we have from point A being our substation to point B being our POI on the grid. In this case, this would be our point A, and then following the line here, this would be point B. So in this case, we're saying our required power factor should be 0.98 right here. And our capacitor bank, again, looking back at that model, will be compensating for any reactive power that we have in our system from here at the substation input to our grid here on the output. So we have the understanding here of our connection type being our substation, and secondly, our overhead line as being the infrastructure that's directly going to contribute to helping to ease up some of the grid saturation here and being sized appropriately for any sort of expansion and agreements that we have with the utility. And then directly affecting our grid saturation here is our cap bank and making sure that our power here is clean and made majority able to be used for the end user here, making sure that we're in accordance with our regulations and for actually having power that can be utilized here by end users. Getting into the last portion here, and certainly not least, is the actual BESS solution or our battery energy storage system. So we always have two options here, AC BESS, and again, a recent add of DC BESS. For the purpose of today, and really the major contributor here in terms of the actual grid saturation and aiding that, AC BESS is going to be our best friend in this case because we have direct control to charge and discharge from the grid at large, whereas DC BESS is going to be more localized to our system and typically used for smaller projects. In selecting our BESS, we have the ability to select our PCS, meaning here our inverter that's going to convert from AC from our plant to DC that'll then charge up the battery, and then vice versa when it goes out and we're actually say discharging into the grid from DC from our battery back to AC, which then can flow out to the grid. So being able to select our inverters per PCS, then choosing the battery container here. Again, I would take a nameplate or say a cut sheet to be able to pick whatever battery that we so choose, and either sizing here on the container size of how many kilowatt hours it's going to be, or if we want to, we can get into the individual racks. For BESS requirements, we can either choose one or two options. In this case, I just chose maximum capacity, saying pvDesign help me to, given my footprint of my BESS area, maximize the amount of power that I can store and then send out at a later time or absorb here, given the footprint that I have. Looking over here on the very right-hand side, I can see directly how much that I'm actually able to store or use. And the area that I drew is quite large, especially in accordance to the power here for my plant at a total of, say, 190 megawatts AC with a BESS capacity of a whole 261 and change megawatt hours with a supply duration of about 1.4. Obviously, this is very, very large in accordance to my PV plant, but just as a demonstration here as to how we might size things. And if we're using this really as a combination in terms of being able to store up a large amount of power and discharge at a later time when the grid is really in need, this is something that can really provide relief to the system and reduce that grid saturation. And vice versa, if we have an excess of power, on the grid at any certain point, maybe during midday when everybody is at work, we can again absorb any extra power that isn't being produced by our plant in this case. And then lastly here, we can get into the BESS layout. This is largely going to be a proponent again of whatever our cut sheets are for PCS and battery dimensions. So I won't spend all too much time on that here, but just know that we can adjust this to make sure that our footprint is actually going to match for our BESS to our area here. And then we can set our distance in between the blocks. Just as a little word of warning here, we do have the NFPA 855 standard being applied, so that we're going to meet those minimum criteria, but of course feel free to make it larger depending on whatever standards that you adhere to internally. And last but not least, this is a newer feature as well, having the battery placement either be horizontal, vertical, or rotated. You'll see mine are just rotated ever so slightly from 90 degrees here from the vertical line, just because I drew my box a little bit haphazardly here for my BESS footprint. But of course I can change it vertical or horizontal, perhaps whatever gives me the best yield, or in combination with the roads that I'm going ahead and designing around my site, this would be impactful for me. Again, the combination of all four elements, so our infrastructure that's going to directly be able to carry that capacity, that added capacity over the line, both in terms of a source and a sink, being the overhead transmission line and the substation. Again, very important electrical components. And then thinking here about the actual power factor, making sure that our power is clean and reliable for our end users, and we're not going ahead and clogging up the lines with a large amount of unusable power. And then lastly here, our best solution that can act again as a source and a sink, providing power to the grid at times when it needs it most, and absorbing power from the grid and from our actual PV plant when we don't necessarily need to supply it to the grid. And that's what I had for showing you here, how we can actually implement everything here in pvDesign. So I'm just going to go back to our webinar page, and we can get going on our Q&A section.
Perfect. Thank you very much, Nick. That was really clear, even for me, and I'm not technical. So thank you very much. On the right side, guys, you have the chat version, the question. Read as many as you want. Okay, we already have a couple that I'll go ahead and ask in a second. Just to give you some time to think about any questions that you have, I wanted to let you know that we will also send you a recording of the session of today and some materials for you to read over. If you have any thoughts, you can always write us, okay? So that being said, let's start with the first question. Nick, if you're ready. So they're asking about where will the capacitor bank be installed if I choose to utilize the equipment to correct the power factor?
That is a great question, and honestly, one of the first ones I had personally when pvDesign first implemented the use of capacitor banks. So I think it best if I maybe go ahead and illustrate it here in pvDesign. So here I'm back at my site design, and I'm showing here my latest and greatest design where I have my BESS implemented, I have my substation, right? I have my transmission line, and then here's our end POI or point of interest at this adjacent sub. And then I went ahead and introduced in grid point and grid requirements for that size and for power factor, I said I'm going to use that cap bank. Now, a common mistake would think that wherever this blue dot I choose is going to be where the cap bank is installed. That is actually not the case. The cap bank is always going to be installed at the substation input, which just so happens to be where I chose for the implementation of correcting for the power factor. But even if I say chose my schema here to be for the substation output, we're going to see the actual capacitor bank physically be implemented here at the substation input. And so I can show that here by just say selecting done, run the design, and then I'm just going to quickly save this. Finish up, and while that document is generating, I'm just going to head over here to our knowledge base, again, kind of our internal encyclopedia of all things pvDesign, move to the methodology section, and then go here to the power factor methodology, open up this manual here, and then just going into the different contents, I can go to capacitor banks in part 4. And now we can see our capacitor bank here in this 4th section is always going to be implemented here, right between our medium voltage system and our high voltage system here at the beginning of the substation. And then if we're curious as to, how it actually factors into correcting for the power factor, we have a bunch of different calculations as well as our phasor diagrams for understanding exactly where it'll be implemented and how it's actually going to be correcting that power factor, so we can better understand how the system impedance is being accounted for and corrected. We'll have this in the case that we actually use the cap bank, or if we're just correcting for the power factor with our inverters, we'll have that as well. And then similarly, if we open up any piece of our documentation, say for example, I want to go ahead and look for my interconnection facility single line diagram, I'll quickly just download this PDF. One second here as I get logged back in.
While we do this, I can just mention for everybody to know that you don't need to be a client to actually access all of the methodologies. They're open in the public for everybody to study. So yeah, feel free to read out.
That is a great point and something we should probably provide in the follow-up email so everybody can have a link to go ahead and really check under the hood, if you will, as to all things pvDesign and how we're performing these calculations. Of course, want to be confident in our methodology and in our calculations that we're providing. So in my selection here of the substation layout, we can see that double bus bar config that I had selected earlier, and then going directly here to our capacitor banks, we're going to see 2 of them implemented again here at the MV switchgear level, so at the entrance really here of our substation. And then if I zoom in close enough, we can see where they're actually sized. So it looks like this one over here on the left being about 1340 kVAR.
You might need to zoom in a little bit more.
Okay.
I think
if
you
we're
can.
Oh,
okay.
I know it's a little bit small, but here I'll promise I'm reading the values. It looks like about 1340 kVAR on the left-hand side and about 1540 on the right-hand side.
Also, FYI, this can be also downloaded in AutoCAD. So if you want to zoom in as much as you want or change things, you can always do that editable version.
That is a great point. We're not limited just to the PDF here. In selecting any of our documents for download, we're going to have both an editable format, say like a docx, like a Word doc, Excel, KML, DXF, DWG, you name it, we'll have that available.
Perfect. Should I go with the second question?
Yeah, please.
Perfect. Let's get to it. So the team is also asking, going back to the battery storage section, how could I design an AC coupled battery storage solution? And they specifically say sized at 20 megawatts AC, 40 megawatts hour, with a duration of 2 hours. Let me know if you need me to repeat those numbers specifically.
Okay, I just pulled up the question here so I can call back to it. Great question, and this is one that I actually get quite commonly in working with other people. Here you can see that again, when I set this up originally, I just went for maximum capacity, and I have this very large and maybe unreasonably sized BESS system for my actual PV plant. So I can show maybe a more practical application for a plant this size in terms of actual sizing things. So I'm just going to leave my storage inverter as is. So with a nominal and a Pmax kVA of 1000, and then just leaving my inverters per PCS at 2. Just multiplying those two numbers, 1000 times 2 is going to equal our 2000 kilowatts is going to be our power per power conversion system implemented here. That being shown in this green icon right on my cursor. And then for our battery container, this is going to be a little bit set in stone, depending on what battery manufacturer, make and model that you choose. But if I wanted to create some nice kind of round numbers for us here today, let's imagine that I want to use this 1000 kVA storage inverter. And then I was also planning on using, say, a 4000 kilowatt hour container or battery container. In selecting those two, you can see here that I'm starting to alter my choices here. And then for BESS requirements, in this case, having instead of the maximum capacity, again, we're still getting around 210 megawatts. Let's choose here for a specific capacity. So here we can directly select how many PCS we're going to implement. And then, of course, that is going to directly result in how much rated power that we're actually going to get out of the site. And so since we have 2000 kilowatts per PCS, if I say do a nice round number of 10 and then click run design, we should be able to get to the numbers that we're looking for. So again, 20,000 kilowatts here, equaling that 20 megawatts AC. And then our battery capacity or BESS capacity being 40 megawatt hours as a function of how many hours our supply cycle duration is times our BESS rated power. And then our supply cycle duration here being in nice round numbers and increments of 2. So 2 all the way up to 24 in this case. Our minimum amount here that's going to be calculated is again just going to be a factor of our battery container divided by our PCS. So just looking at the units here, since we have 4000 kilowatt hours, dividing that by 2000 kilowatts, we're left with 2 hours. And then that's going to equal our minimum in terms of the supply cycle duration. If I were to say reduce this to 2000 kilowatt hours, then my lowest hour increment is going to be on increments of 1. And here we can see on my output, I have the 20 megawatts, 40 megawatt hours, and 2 hour supply cycle duration. All right, Laura, do we have any other ones?
Thank you for that explanation. I think people are a bit shy today, but feel free to reach out as many questions as you want. Today is the day to have the expert here to explain it to us. Having said that, we don't have a lot of time either. But there is one question that asks, what does the double bus bar offer? I don't know if you can get a little bit into that.
Yeah, the double bus bar offers a bit more reliability and robustness in terms of the design. So let's say going back here to our methodology section, and we can get into our interconnection facility methodology. Again, this is open to everyone, even if you don't have pvDesign. Here we can look into our coordination of the substation, equipment, as well here as, let me find it, design of the bus in the air. This will allow some calculation and some explanation here of the actual, say, bus and buses. Just looking at things in terms of the document, if I actually go ahead and open up here, again, my single line diagram, looking at the double bus bar, here you'll see that we have these different switches allowing us to switch in and out of these double buses. At all points, we won't necessarily have to use the double bus to be able to contain our power on a nominal basis. But should there be any sort of electrical issues on, say, one of these buses or one of these other pieces of equipment, it would be really nice to be able to have essentially a backup or another layer here so that we can rely on another bus. So imagine there's some sort of electrical fault on this bus, perhaps a tree branch hits it, or some other sort of catastrophic event. Our circuit breaker here would likely open, protecting our rest of equipment. Same thing here with our disconnector switches, in which case we're going to have to isolate this bus, but we can continue operation if we open all of our safety equipment, say utilize this bus here at the bottom, as long as it's sized up to be able to contain our entire system, and then continue on with normal operation. Say we had just a singular bus bar in that case, we're going to be down for X amount of time, essentially until we can get an electrical crew out there and someone to help us to actually fix the problem, which can mean a lot of losses, both in terms of energy provided to the grid and of course profit if you're going to be the owner and operator of that PV plant.
Perfect. Thank you. Okay, so I believe we're gonna send you the presentation of today. There you're gonna have both of our emails. So feel free if any questions just come up later on in the day or in the week, just let us know. Feel free to reach out, okay? Having said that, thank you for being here today. We appreciate a lot your time and hope you found it interesting. Thank you, Nick, for your time too. How was that?
Awesome, thank you all. It was amazing. Great to be on here and great to see you all. Hope to see you again soon and hopefully support you if you're on the pvDesign side.
Perfect. So there are no more questions. I think we can wrap up for the day. Again, have a great evening, day, or wherever you are. Have a good day.